Hello, and welcome to the second of our 2020 Mighty Low Carbon Energy Center webinars, and our first ever virtual webinar. I'm Robert Stoner, the Deputy Director of Mighty for Science and Technology. Our intention in presenting these webinars is to cover a range of topics drawn from our ongoing work in all of Mighty's low carbon energy centers, and a few drawn intentionally from outside them. We want you to know what we're up to at MIT, and what we think is especially interesting and important as we work toward a globally decarbonized energy system. And because we want to engage and hear from you, we've chosen to present live and to reserve some room at the end of the webcast for your questions. You can pose your questions at any time in the Zoom webinar format. Just type your question after clicking Q&A at the bottom of the screen. We'll see it. We've practiced a little, and our expectation is that video will focus automatically on the speaker at the given time, and we really hope it does. As usual, we'll be recording this webinar so that you can review the material at your leisure and also pass along a link to your colleagues. We hope you will. And so without further ado, in today's webinar, I'm delighted to host Randy Field, the Executive Director of the Mobility Systems Center, our most recent Low Carbon Energy Center, and Joanna Moody, the Research Program Manager of the Mobility Systems Center. Their topic today is the future of mobility. And so without taking up any more of your time, Randy and Joanna, let's shift the focus over to you.
Thank you very much, Rob, and thank you all for joining us today on this virtual webinar. As Rob said, we're here to discuss our analysis about future mobility. This is a culmination of 3 years of research that we've conducted at the MIT Energy Initiative, and our report is called Insights into Future Mobility. And in this study, we were motivated, of course, by the ongoing challenges in the mobility space and the desire to understand how the mobility landscape will change under these various drivers. These drivers include the fact that over the coming decades, there'll be more than 2 billion more people on the globe. And this fact, in combination with the fact that income is rising around the world, means that you have more income with which to address people's increasing demand for mobility. This will increase both demand for mobility and for energy that is required for mobility. Now we recognize that with mobility comes various challenges. We have challenges of pollution, climate change, congestion, fatalities on roads, and many other types of challenges. We also have drivers including issues of technology, new technologies, new business models for mobility, and we also seeing the evolving forces of governments' policies that affect climate change, pollution, congestion, and so forth. So we were motivated to begin this study more than 3 years ago, and we broke this down to 5 areas of inquiry. First of all, we were looking at the impact of how climate policy could affect the light-duty vehicle fleet in terms of the fleet composition, meaning the powertrains of those vehicles, the fuel consumption, fuel prices, and the economic output. We also took a close look at the outlook for vehicle ownership and miles traveled in the United States and China, the 2 largest markets in the world for the light-duty vehicle fleet. We also examined the techno-economic and emissions associated with alternative powertrains and fuels. So in that, we looked at internal combustion engine vehicles versus battery vehicles versus fuel cell vehicles to understand how the emissions differ in these types of vehicles. We also understand the importance of infrastructure for fueling and charging vehicles. There's this chicken and egg problem that people will not buy a hydrogen vehicle or electric vehicle if they don't have a clear way in which they're going to fuel those vehicles. So we looked at that, those dynamics and the importance of infrastructure and the evolution of the vehicle fleet around the world. And we also examined the disruptive role that lower cost ride-hailing services would have in urban settings. That was another piece of the study. And the entire study is available to you online at this address. In today's session, we're going to take key portions of the study and share them with you. So first of all, we examined how the light-duty vehicle fleet will evolve in the context of global economics and climate policy. And the key framing question for this part of the work was to examine the impacts of different climate policies on the energy demand, on the economy itself, and on the vehicle fleet mix. To do this analysis, we used an economic modeling tool, our computational general equilibrium model, to examine the world economy. This is a model of the global economy, breaking down the world into different regions in which there's trade between these regions, and of course into different segments, including the electricity segment, transport segment, industry segments, and the others, which all interact with each other. And within the transport sector, we looked at we represented the relationship between income growth and demand for transportation. And we also represented the vehicle fleet within that model in terms of vehicles, vehicle age. And within the vehicle choices, we identified different powertrains and the trade-offs between them, both in terms of the purchase price as well as the fueling costs. So that allowed us to examine electric vehicles versus internal combustion vehicles in a global scale. So using that modeling framework, we asked the question, well, what if you have three major scenarios, and how would the world look under these three different scenarios relative to each other? So our first scenario is what we call the reference scenario. Basically, this is saying, well, the world existed without the Paris Agreement, and no additional policies were implemented beyond what was already in the books. What would the world look like? The second scenario, what we call the Paris Forever scenario, we say if all nations fulfill their commitments that they made in the Paris Agreement, and they fulfill those commitments out to the year 2030, and then continue with those same actions beyond 2030, but added no additional policies beyond those commitments, what would the world look like? And third, we looked at the Paris Forever, where we said, okay, all of the nations fulfill their Paris commitments out to the year 2030, and then after 2030, the entire global economy goes to a carbon prices across all sectors of the economy, across all nations. And so that gives us a very contrasting view of the world, and allows us to examine what the implications would be for transportation as well as the other sections of the economy. I also list some of the subcategories we considered in the study, including what if the cost of battery electric vehicles is lower? What if there is a greater support for renewables for electricity? And what if there was a fuel cell mandate? How would each of these scenarios impact the deployment of the vehicle fleet? So let me take you to some of the results. In this chart on the left, I'm showing you the entire light-duty vehicle fleet across the globe. And so what you see is that in the year 2015, the vehicle fleet was roughly 1.1 billion vehicles. And we see in all three of these scenarios that the vehicle fleet is increasing substantially into the vicinity of about 1.7 billion. Now, what we're seeing is in the reference case, where there is no new climate policies, that gives you the greatest growth because there's less of a headwind against vehicle purchasing. Whereas in the case of a 2°C scenario, we see a more substantial, we see less growth as a result of that, less growth in the vehicle fleet in that situation. Now, if we look across the world, of course, we see the highest growth in vehicle fleet in China. And we also did some other scenarios where we saw even further growth of the China fleet. But this is just one of those representations for the Paris Forever scenario. So with that, let's now consider, well, how many of these vehicles are electric? So on this diagram, we show those numbers. What we're seeing is that a few years ago, our vehicle fleet that was electric was so small you can barely even see it on the chart. That was about 1 million electric vehicles globally in the year 2015. And what we're seeing in these three different scenarios is that number will increase by more than a factor of 100, going to somewhere between half a billion and 0.8 billion electric vehicles out in the year 2050. So this is, let's say it's very substantial growth, but you also notice that, no, this does not saturate the world market for vehicles. The world market for vehicles, you have to recognize one point is that vehicles on average have a life of about 15 years. And so any change that you make today takes some time to overcome the inertia of the existing vehicle fleet. So that's one factor to consider. But also there are various factors, including cost and convenience, that certainly slows down how much penetration we have. So just to give you a point of reference, in the case of the reference case, the penetration of electric vehicles is about 33% of the global fleet in the year 2050. And it is about 50% for the case of the 2°C scenario. Now you can look at this also globally, and China, of course, leading the way in terms of growth of the electric vehicles in their fleet, followed by the U.S. and Europe. So what does this all mean for CO2 emissions? The first thing I want to point out is that if we have no policy whatsoever, of course, CO2 emissions will continue to climb. And I want to make sure I'm clear that this is CO2 emissions from all use of fossil fuels, both for transportation and for electricity and for industry. So this chart is not exclusively for transportation, but it includes transportation. So we see growth in the case of the reference scenario. If we go to the Paris Forever scenario, basically you see emissions roughly flat going out to the year 2030. Now I'll point out that in reality, over the last 4 years, the CO2 emissions have not been flat. I realize that this year will be a special year in which the CO2 emissions will very likely decrease. But overall, that was not part of our model, and our projection is relatively flat under the Paris Forever scenario. And then after 2030, it starts creeping up again, since we will not have had, we are assuming no new policies at that point in time. Whereas, as shown in the golden curve here, after year 2030, the world gets together and agrees on a global CO2 price that goes into all sectors of the economy, and that will dramatically decrease the CO2 emissions. And that's where we saw impact on the vehicle fleet in the last few slides. It also, I want to point out that these reductions in CO2 emissions from light-duty vehicles, it doesn't come exclusively from electrification, but it also comes from the very important side of fuel economy improvements for the internal combustion engine vehicle. As I showed you, the life of these vehicles and the penetration of electric vehicles doesn't happen overnight. Therefore, it's very important that the world continue to improve fuel efficiency of internal combustion vehicles while we simultaneously go to electrification. So key takeaway messages in this, this piece of the work is we showed that in all of these three scenarios, we will still have substantial growth in the global economy as well as in the US economy. So what that analysis demonstrated that although there's some drag in the economy due to policies that mitigate CO2, you still end up with substantial growth over that period of time. We are expecting substantial EV penetration over the years ahead, but that adoption rate is directly dependent upon government policies. As I stated, in the reference case, the penetration globally to the fleet is about 33% for the reference case versus 50% for the CO2, for the 2 degrees C case. The other observation is that transportation alone is not a solution to the problem. This is a really concerted across the globe, across the economy solution that requires not only decarbonization of the fleet, but also simultaneously decarbonization of the electric grid. Because if you're going to have electric cars, you have to have decarbonization of the grid as well as manufacturing and other sectors of the economy. And this global economic model helped us to illuminate that. And therefore, of course, climate policies need to address all sectors. The next point I want to make is cost. Of course, the economic model I just showed you is cost driven, but we want to illustrate the very important question of how cost for battery electric vehicles is a key factor in determining the uptake rate for battery electric vehicles. We recognize the battery is a major cost for these battery electric vehicles. Furthermore, the price of batteries has dropped very rapidly over the last 10 years, and yet it is still a major contributor to the cost of the battery electric vehicles. We know that as production volumes increase, the trend is for the battery prices to drop further. But the major question is how low will the price go and how quickly will the price drop? We know that as the price and the cost of the battery electric vehicles approaches the cost of the conventional vehicles, the battery electric vehicles expected to have a much stronger market share, even if you take away mandates and subsidies. So we therefore took a very close look at the price trajectory for batteries that are needed for the BEV vehicles. And it's quite common for people to examine future cost of a technology or a product by using learning curves that then make a relationship between the volume or number of units manufactured relative to the cost. And the basis is that as you make more and more of these units, the price per unit drops. We took a more detailed look at this and said, well, let's look at the overall supply chain for manufacturing a battery. So if we start with the mining operation, you've got to mine your nickel, your cobalt, and your other minerals. Then you have to process those minerals into their active ingredients that will then be fabricated by a manufacturer into cells. And those battery cells then are combined into a battery pack, which then go into the electric vehicle. So we basically broke this down into a two-stage learning curve. First stage is the material synthesis, and the second stage is the battery manufacturing. And we examined the data over the past years and determined that of course, mining is a very old industry, and a lot of learning has already been worked out of that in a major way. And so what we see is a learning curve, the rate at which costs decrease. That learning curve is relatively small with LR 3.5%, whereas the manufacturing of the battery pack and the battery cells is much higher with a learning curve of 16.5%. What this tells us is that even though we've had very rapid decrease in the cost of battery manufacturing over the past 10 years, what this means is that that rate of improvement will not continue on a log scale. What you actually have is a larger and larger portion of your cost being the materials as opposed to the manufacturing of the pack itself. And that creates what we refer to as a floor price. And by having a floor price, you're recognizing that the price of the battery never gets to zero, even if you make an infinite number of units, which of course is a good reality to have. And so what our analysis says is that there's a great deal of uncertainty about the future price of batteries out in the year 2030. But our expectation is that it's likely that the cost of the battery for lithium ion batteries in the year 2030 will remain above $100 per kilowatt hour. Now, using those projections, we went on to ask the question of, well, what does this mean for total cost of ownership of a vehicle? Because basically, at the end of the day, light-duty vehicles are predominantly purchased by households and individuals who are looking at their own economics. And so, and what's best for them. So you basically have the total cost of ownership made up of the purchase cost and the operating costs. And the purchase cost includes the purchase taxes, and of course, if there's any subsidies removed. Operating costs include your fuel costs, insurance costs, maintenance costs, and battery replacement. So we examine this with a certain set of assumptions that the vehicle lasts 150,000 miles, no battery replacement, certain price for gasoline, certain price for electricity. And we compared an internal combustion engine vehicle versus a hybrid versus a plug-in hybrid versus a battery electric vehicle, and examined the vehicle cost, fuel cost, maintenance, and insurance, each of those. And what we see, if you have no subsidy and you're in the year 2018, that higher purchase cost for the battery vehicle puts you at a disadvantage relative to the internal combustion engine vehicle. That's even though the fuel cost for the battery electric vehicle is substantially less than the fuel cost for the internal combustion vehicle, and even though the maintenance cost is substantially less than the maintenance cost for the internal combustion engine vehicle, which has a lot more moving parts, a lot more annual maintenance fees. Now, that's only useful to look at 2018. What's more important is where will this go in the future? So for that, we took the data on our projections for future battery costs and said, well, 2018, if the battery cost is more than $200 per kilowatt hour, we're looking at a substantial price premium for a battery electric vehicle or a hybrid plug-in vehicle relative to a cost of a internal combustion engine vehicle. Now, as you slide to the future, of course, the cost of batteries comes down. And if you want a battery electric vehicle with more than 200 miles on it capacity, then you're talking about more than $7,000 price premium relative to the internal combustion engine vehicle. If people were willing to have vehicles with lower range, that number would be lower. But the point is that even with the projected drop in the price of batteries in the years ahead, that purchase price without subsidy is higher than an internal combustion engine vehicle. But as I said, the cost of maintenance and the cost of fuel does come into the picture. So if we look out, if we look at the picture in 2018, you look at what's very important is what is the actual price of gasoline, what is the price of electricity. So this chart shows me my parity lines. And what this says is that if you're in the United States and your average purchase price tax on a vehicle is a blue line is 7%, then that says if your gasoline price and your electricity price is below that parity line, you're better off buying a internal combustion engine vehicle. Whereas in Norway, where the price of gasoline is very high, you're now sitting above the parity line, and your purchase cost over there is your taxes on a purchase may be higher, but in Norway, basically, you'd be better off with a battery electric vehicle, and of course, the penetration in that country is very high, in particular for that reason. So, cost of fuel is very, very important in this equation. Now, if we jump out to the year 2030, it's a very different situation now that the price of the batteries is about $124 per kilowatt hour. Now, in most countries of the world, where there's a higher price for gasoline, without any subsidy whatsoever, these vehicles will tend to be, the battery vehicle will be less expensive in China, Japan, Europe, whereas the US will be right on the borderline. And I want to make the point is that there's a great deal of sensitivity, a lot of assumptions in this economic, in this cost model. And I just want to illustrate the, in this tornado diagram, the battery costs have a great deal of uncertainty. The gasoline price has great uncertainty in terms of where you are in the world, as well as government policy, electricity range, all these have major factors. And so what this says is that in the future, we're going to be within a 10% range of what we call total cost of ownership parity. And at that point, it really is no longer a question of cost. It's much more a question of convenience. So what it comes down to is that today, both economics and convenience currently favor the internal combustion engine vehicle over the battery electric vehicle. But if China sticks to its declared mandate in production of electric vehicles increases substantially over the decades, over the next decade, that will help drive down the cost of batteries, and the total cost of ownership will be quite comparable between the internal combustion engine vehicle and the battery vehicle in the United States in the year 2030. And it will be much more favorable for the battery electric vehicle in other parts of the world where prices of gasoline is higher. Now, once you get to parity on price of the vehicles, cost of vehicles, it really becomes a question of range anxiety and charging convenience issues, in which case it's very important to have the infrastructure out there to support whichever type of vehicle people are investing in. So with that, two topics covered, I'd like to now hand off to Joanna Moody, my colleague on the Mobility Systems Center, to take these next two topics. Joanna?
Great, thanks, Randy. So I'm going to talk a little bit about life cycle emissions of alternative fuel vehicles. And this analysis is really based on data from the United States. And really the driving question to this part of the study and the research was, what are the complete life cycle greenhouse gas emissions from different vehicle types? So from an internal combustion engine vehicle, from a plug-in hybrid electric vehicle, from a pure battery electric vehicle, and how do they compare to one another? And in order to do this analysis, we chose similar car models for to really minimize the differences in the non-powertrain features of these different vehicles. So you're going to see that we're looking at an internal combustion engine vehicle, a hybrid vehicle, a plug-in hybrid vehicle, a battery electric vehicle, and a fuel cell, a hydrogen fuel cell vehicle that all have very similar interior volumes. So they're similar size, similar weight. And so that's really minimizing any of the vehicle characteristics and really looking at just the emissions that are different because of the powertrains, how they're fueled and what powers them. So next slide, please. All right, and so we're gonna look at a full life cycle of these vehicles and the fuels that they're consuming. And so we're gonna start from the raw materials extraction and the production of the fuel that goes into those vehicles. We're also going to look at the manufacturing of those vehicles themselves, and then the use of that fuel in the driving, so the end use driving. And then there are some life cycle emissions from end of life recycling of those vehicles as well. And so we're taking a really broad system boundary when we're looking at these life cycle emissions. Next slide. And here is how the different powertrains compare in the US today. And so you'll see that the internal combustion engine vehicle has the highest emissions per mile traveled. And the battery electric vehicle has the lowest emissions per mile traveled. And this is using the US average electricity grid. And then we have the hybrid electric vehicle, the plug-in hybrid electric vehicle, and the fuel cell electric vehicle are all somewhere in the middle, in between the internal combustion engine vehicle and the battery electric vehicle. And so given the carbon intensity of the US grid today, you are better off in terms of your life cycle emissions driving a battery electric vehicle than you would be driving a comparable internal combustion engine vehicle. And I'll note here that these fuel cell electric vehicle emissions are based on using steam methane reforming, that's the SMR on this slide, without any sort of carbon capture system or technology. And that is the most common way of producing hydrogen in the US today. Next slide, please. But these GHG emissions for the different vehicle types are extremely sensitive and particularly sensitive to the way in which the fuel or power is produced. And so looking here at the sensitivity of the battery electric vehicle to carbon intensity of the power grid and the fuel cell electric vehicle sensitivity to the hydrogen production method. And so on the previous slide, we had these nominal cases. We had the battery electric vehicle with average US electricity grid. We had the fuel cell electric vehicle with steam methane reforming without any carbon capture. Now, if we look at the battery electric vehicle life cycle emissions, and instead of the US average grid, we take the grid of the lowest carbon intensity electricity of any state in the United States, and that's Washington State. Then what we actually see is that you already have a pretty significant decrease in your life cycle emissions if you're driving your battery electric vehicle it's powered by electricity from Washington. Now, if we compare that to the highest carbon electricity state in the United States, which is West Virginia, which has a high amount of coal in their electricity production, then we actually see that you're worse off than driving a hybrid electric vehicle. You're about on par with driving an internal combustion engine vehicle. But really what this shows is that even with the grid today in the United States, there's a four-fold difference in the life cycle emissions, depending on whether you're charging that vehicle in the lowest carbon intensity electricity state or the highest carbon intensity electricity state. And then we also look at China, where we have the largest growth and huge government subsidies and push for vehicle electrification. And we see that their electricity grid has a fairly high carbon intensity, not quite as high as West Virginia, but higher than the US average. And so in terms of your greenhouse gas emissions impacts of electrification, really the greatest benefit would come if China can also begin to green their grid. And we see a very similar story with fuel cell electric vehicles when it comes to their sensitivity to hydrogen production. So while conventional steam methane reforming without any carbon capture is the current way in which hydrogen is produced, if you were to move towards steam methane reforming with carbon capture or electrolysis with a very low carbon intensity electric grid, then you start to have fuel cell electric vehicles have very similar greenhouse gas life cycle emissions to battery electric vehicles. So really, both of these can have significant reductions on the greenhouse gas emissions of the light duty vehicle fleet, both fuel cell electric vehicles and battery electric vehicles. But again, this really comes with a coupling of the decarbonization of the energy source that's being used to move these vehicles. Next slide. And so now I'm going to talk about the last piece of work within the report that's focused on motorization and urbanization, and sort of what is the role of some of these new technologies and services that we're starting to see emerge on our city streets. Next slide, please. So Randy talked a little bit about the growth in the total population of the world and sort of the growing demand for mobility. Now, within that, there's also increasing urbanization. So while our population is growing, we're also increasingly concentrating within cities. So the United Nations estimates that the global urban population will go from about 4.7 billion people today to 6.2 billion by 2050. That's an extremely huge number of people moving into our cities. And with those, and as they move into cities, their incomes grow, and so does their demand for mobility. Next slide, please, Randy. So as their incomes grow, so does their appetite for car ownership in particular. So we're starting to see that we have fairly rapid motorization, particularly in Asia, Southeast Asia, and in Central and South America, with Africa emerging as sort of another market to come in the next decade or 2 decades. Next slide, please. But motorization is driven by much more than just rising incomes. While car purchase power is an important factor, we also know that the car is an aspirational good. And in this study, what we did was we defined car pride as the attribution of social status and personal image to owning and using a car. And we were able to measure this symbolic value of a car and how much it influences people's decisions to own and use cars. So next slide, please. And we first looked at this among individuals in 2 US cities, in New York City and in Houston, Texas. So chosen to be very different urbanization and sort of transportation patterns within US cities. And actually what we found is that among individuals in both of these cities, so these conclusions hold true across both the entire sample and within both city samples separately, that car pride is strongly predictive of car ownership. And in fact, we can compare the magnitude of car pride's impact on car ownership and the magnitude of income's impact on car ownership, and we find that they're about the same. And that means that while we often use income to predict growth in car ownership, this aspirational or social status symbolism is as strongly predictive of whether or not someone will own a car. And that car ownership then enables greater car use. And then car use actually reinforces car pride. So the more that I drive my vehicle, the greater my symbolic attachment is to that vehicle. And this is all true after controlling for the sociodemographics of these individuals. And so what we really find is that there's this reinforcing cycle among car pride, car ownership, and car use. Next slide, please. And then what we did is we measured this same construct of car pride across a sample of around 42,000 individuals in 51 different countries. And here are the country car pride. So this is for an equivalent individual living in this country. This is the effect of that country on their car pride. And so what we're finding is that I've colored these based on whether the country is considered developing or developed by the United Nations. And so what we see is that the dark purple down closer to the bottom show that a lot of the developed countries, particularly in Europe, are showing much lower car pride, and that actually the highest car pride that we're seeing are in the Southeast Asian and African countries that are rapidly motorizing or are coming to the point where they will be rapidly motorizing. So this really suggests that this aspirational or symbolic value of a car may drive car ownership or appetite for car ownership even more than what we would predict with just growing incomes alone in these regions. And I will note that the dark purple outlier is the United States. So among the developed countries, the United States has the highest car pride. Not surprising for me personally, having lived here and experienced and worked with this. Next slide, please. So this is a little bit alarming if we're going to be adding over 2 billion people to our city streets. And there's really no way, just in terms of physical space limitations and geometry, to accommodate all of this growth in people and their mobility demands by private car. And cities are already plagued by negative externalities of ineffective urban transportation systems, including congestion, air pollution and greenhouse gas emissions, road fatalities and injuries, and issues of social exclusion. So the question is, how can we accommodate this growth in mobility and get people where they need to go in our ever-growing cities in a way that doesn't rely on the existing paradigm of private car ownership and use? Next slide, please. And now there's a number of emerging technologies and service innovations in this space to try and address this issue. And we've talked a lot, both Randy and myself, about alternative fuel vehicles, battery electric vehicles, fuel cell electric vehicles. I'm not going to go into those here. We're going to touch a little bit on autonomy and connectivity, and then also service innovations like on-demand ride hailing, your Uber, your Lyft services, and sharing and pooling. So this is the idea of dynamically adding multiple trips within the same vehicle. Next slide, please. Now, emerging technologies and services have real benefits, but if they remain within the car form factor, their abilities to mitigate congestion, and this is again that physical space demand, are limited. So you'll see here that this is an image of how much space is required to move 42 people in a single occupancy conventional car. If you move over, you see it takes the same amount of space to move 42 people if they're a single occupant in an electric car. You move over and you'll see that it takes the same amount of space to move 42 people in an autonomous car. And if you move over again, if you have on-demand private rides where you're only counting the 42 trips or the passengers that are being moved and not the drivers, then they take the same amount of space to move 42 people. And so this should be concerning that these new service and technology innovations cannot address this issue of limited space as they're being imagined now. Next slide, please. And so really what this means is that in order to move more people in our existing space in urban spaces, we need to encourage mode shift and behavior change, and that has to be part of the solution. And so here's the same 42 individuals, rather than in a car, whether that car is electric, autonomous, or on demand, here they are walking, biking, or taking a bus. Now, if you were going to depict a train, that would be sort of even less space taken up for the amount of people that you can move. Next slide, please. Now, I often get a lot of pushback on this, and people say, well, what if you were to combine these all together? That these service innovations and these technologies are not meant to be deployed one or the other, that we're looking at envisioning an on-demand shared fleet of electric autonomous vehicles. Well, what we did is we had a group that has an agent-based, activity-based, multimodal micro-simulation of all of the trips and demand for travel within a city. And so what they did is they looked at a couple of scenarios. So the base scenario, which was the existing demand and transportation services in the year 2016, they looked at a scenario where they introduced this autonomous shared mobility on demand service that runs on electric vehicles. And they introduced, and then they run another scenario where they introduce this, but they require through regulation, or sort of in this case, just constraints within the model, that these services have to provide first last mile service for public transit. And they're going to simulate these same three scenarios in three different city types. An auto sprawl city, you can think of a US city like Baltimore or Houston, what they call an auto innovative city, you can think of this as Boston, and then a mass transit city, which is something like Singapore or New York City, where you have pretty high existing public transit network coverage and ridership. Next slide, please. And what we find is that if you introduce this low-cost, on-demand, autonomous mobility service, you increase congestion and you increase vehicle miles traveled. So we see that while the private car mode share does drop a little bit, some people do switch from their private car to this new service. We also see drops in public transit mode share. And that results in an increase in congestion and an increase in the VKT, the vehicle kilometers traveled on the city roads. And this is true if you have a sprawling auto-oriented city, again, think of Houston, or if you have a dense transit-oriented city, think Singapore or New York City. Next slide, please. But we do find that policies that encourage the introduction of these on-demand mobility services as first-mile connectivity to mass transit can provide some of the mobility benefits and serve additional trips. without some of the negative impacts that we saw in that previous scenario. And so we find that this reduces private car mode share even more and actually increases public transit mode share compared to the baseline. And what that means is that we see sort of some improvement in the overall mobility and number of trips. And this is particularly true in the dense transit-oriented cities, where we actually see a reduction in vehicle kilometers traveled when you're constraining these mobility services to be providing first last mile service. Last slide, please. And really what this suggests is that emerging technologies and service innovations have as much potential to exacerbate the problems in our urban transportation systems, and I would say that's particularly true of congestion, than they do to solve them. And the balance of the benefits and externalities of these new technologies and service innovations are going to be based on how consumers adopt these technologies and services and how their introduction is shaped by policymakers. So going back to that previous slide for a second and just thinking about the impact that requiring these services to provide first last mile connectivity has in terms of a policy lever of switching what the impacts are going to be on the transportation system. And so with that, I will turn it back over to Rob to facilitate the Q&A. Thank you.
Thanks very much, Joanna and Randy. That was really interesting. Speaking of interesting, I was just looking at the number of participants in the call has grown over time. We're now at 44. And I see people from India, Indonesia, Spain, Italy, France, Japan, and all over the United States, which is really kind of fun and I think heartening in a rather strange and difficult period. So welcome to everyone. I see also a couple of hands up, if I'm interpreting the symbol correctly, against a couple of people's names. I don't think there's anything I can do about that or we can do about responding to those hands, but we see them. And my suggestion is that rather than wearing yourselves out, waving your hands around, that you type questions you might have into the Q&A. I hope it's apparent how to do that. There are a couple of questions there, and I'll come to them in a moment. But maybe I could just get things started by asking a question or two of my own. The wonderful and amazing Elon Musk has sort of figured out a couple of important things about electric vehicles. And I think one is that you can bury the cost of an expensive battery in a really expensive car and begin making sales, not to the bottom end as the American car manufacturers seem to imagine, but to the top end of consumers. And I assume they have lots of car pride up in that space too, Joanna. So small cars have never really done well. Small electric vehicles haven't really taken off. There have been lots of models and there are lots still coming out. But what I see Elon talking about now is electric pickup trucks, really expensive electric pickup trucks, and maybe even a few American manufacturers beginning to hearken to that call as well. So that's a very different sort of vehicle from the 5 almost identical red sedans you used in your study. And it might point to different conclusions, at least in the United States, where now very inefficient cars are being electrified. And it suggests to me, at least, that perhaps the cost of ownership would tend to favor electric vehicles earlier in that regime than in the sedan regime. Does that make any sense? And have you thought about that at all, Joanna?
That's a really interesting question.
I haven't rehearsed these questions.
Yeah, so I think there's a lot of different pieces to that. One is that it is true that electric vehicles are starting to provide a lot more choice in the types of vehicles that are on the market. And for a while, it really was limited to smaller compact cars and sedans. But we know that that's less than half of the US car sales today. Over half of the car sales today are in the light trucks and SUV market, where there were really fewer electric vehicle options. And that's pretty rapidly changing. But those larger vehicles are more difficult and more expensive to electrify. They require larger batteries to power them. And given that the battery is still a reasonable amount of the emissions of a vehicle, we would expect that requiring a larger battery would increase the life cycle emissions of a battery electric vehicle a little bit. Now, if you drive that vehicle enough, that could be very easily offset with the much lower carbon emissions in the use. So I think that my gut feeling, although we haven't run the numbers, is that you would still be better off running that larger battery electric vehicle if you can get the energy density that you would need to power it and give you the range that you would need as a consumer. And I think that also brings us back to Randy's earlier point in the presentation, which is that vehicles take a long time to turn over in the fleet, and that we can't expect that we're going to go to 100% electric overnight. And as the trend goes towards, in Europe and the US at least, consumers wanting larger vehicles, those larger vehicles tend to be less fuel efficient. If you're just talking about an internal combustion engine vehicle, so forgetting even electrification for a second, if you are upgrading your sedan to an SUV, that has implications for the next 10, 15 years in terms of global climate change. And so what we really need to see is we need to see electrification, and we also need to see continued improvement in the fuel efficiency of vehicles. And that again comes to sort of consumer choice and behavior change, is that you can make a significant impact just trying to combat this trend, trying to understand why is it that people are moving towards these larger, less fuel efficient vehicles, and how could we get them to maybe change that trajectory, get them to buy smaller vehicles, whether they're battery electric or not, and then those become easier to electrify as we move forward.
There are a lot of questions starting to show up online, 10 of them, and I'll try to get through them. Maybe by compressing a few into one question. And that question concerns second use. The idea that these batteries that are used in cars have to perform at a very high standard, but and ultimately will trigger a replacement, but they're still pretty good batteries and maybe could be sold to people who would deploy them in the grid and get further value from them. Is that value somehow accounted for in the pricing scenarios or cost scenarios that you're thinking about? Or is that an additional benefit that somehow yet needs to be accounted for?
The whole question of what happens to the battery when it's no longer good enough for a electric vehicle is a very important topic, both in terms of its second life as potentially a stationary energy storage for the grid or for other applications. That is something that is being explored. And then of course, eventually the question of what do you do to eventually recycle the materials or not, and what's the consequences for waste disposal. Those are important topics. We did not include the economics of those directly into our calculations here. There are a substantial number of unknowns about the market uptake for the second life batteries. It is certainly something already being pursued, but it was not part of our economics.
Next question, it's sort of different avenue, but a really interesting one as well. What about regional sensitivities? I've noticed in my own hybrid car that my mileage gets a lot worse in the winter than it does in the summer. And I imagine that they sort of have a very different experience in Texas and Arizona than I have. And it must be even worse or more exaggerated for BEVs. Did you do any further analysis of that and notice big differences in economics, for example?
Well, there's been research at MIT looking at the fuel efficiency as a result of location in the United States and elsewhere, which actually calculates the energy requirements as a result of temperature and other factors, as well as the type of road systems, because you also have issues of how hilly is your terrain and what kind of driving are you doing? Is it road drive? Is it stop-start driving, which is of course favorable to electric vehicles? Is the temperature too high, too low? And so Jessica Transick has led a study looking at those questions of vehicle performance under different circumstances, and she has a model that specifically addresses that. Within the context of our study, we looked at the fuel efficiencies of the vehicles on an average basis, and keep in mind that the testing cycle that the EPA has now incorporates different types of conditions to try to capture the range of environmental conditions that are important to the performance of both the electric vehicle and the internal combustion vehicle. So we use that average EPA number as opposed to trying to model the regional impact.
Mm-hmm. About policy mandates. This is the subject of another question. Many cities are beginning to restrict the entry of ICEs into their cores. Did you account for any of those in your projections, or if you did, how might they change things?
So in our policy representation, we did not explicitly capture the city type restrictions on internal combustion vehicles or the future promises about restrictions of internal combustion engine vehicles within countries. Those have been evolving over the past couple years. And our policy analysis did not incorporate those. At one point in time, those were considered quite small impact, but they certainly have grown. And in terms of how many vehicles they would affect, it still remains unclear how many of those government or politician promises will turn into reality. That remains to be seen. And so therefore, as a moving target, we did not incorporate those various commitments about internal combustion engine vehicles being allowed in various cities and countries.
May I jump in real quick to add on to that point? That's very true of the global modeling. So we didn't account for these types of city level policies on the global impact. But we did do a deep dive into city level transportation planning in Chinese cities and looked at the policies of restricting car ownership and car use within these cities. And many of these car ownership restrictions, there are 7 large cities in China which have either a lottery or an auction that you have to enter in order to purchase a new vehicle. So they artificially restrict the sale of new vehicles within those cities. And a lot of those cities have exemptions for electric vehicles from those quotas. And so if you want to buy an internal combustion engine vehicle, you have to enter the lottery or the auction. But if you want to buy an electric vehicle, you don't have to go through that process. And so there are some emerging studies that are looking at how that is increasing people's adoption of electric vehicles within those cities. And we are seeing that the growth rate in those 7 cities is something like 5 times higher for electric vehicles than in the rest of the cities of the country. Now, that can be a little bit misleading because these are also some of the largest and wealthiest cities. So we might expect that they have higher electric vehicle demand just in terms of who lives in those cities. But it is likely that these policies are catalyzing and continuing to encourage electric vehicle sales to some extent in those cities.
There are lots of really great questions continuing to come in, and we're not going to get to them all in our remaining minute. But I hope we can, since we're taking a record of them, we could perhaps ask you to think about them and post answers on the Low Carbon Energy website over the next couple of days, so that people can get an even better understanding of what we're learning about. So just in our last 30 seconds. You're standing up this new center, this new Low Carbon Energy Center. What sorts of topics are you going to be looking at there?
Joanna, I'll let you address that. Yep.
Great. Yeah, so we are the Mobility Systems Center, and we're the newest of the low carbon energy centers at MIT Energy Initiative. And we're focused on ground transport movement of both people and goods. And so we're really building off of the momentum that was created from this 3-year Mobility of the Future study, but also expanding the scope to include freight movement and to include deep dives into some of the other vehicle markets within the world. And so while our Mobility of the Future study focused a lot on the US and China as the 2 largest automobile markets in the world, we're now focusing also on some of these high growth countries where we expect to see growth in motorization and demand for mobility upcoming in the future. And we still continue to have a focus on clean fuels and propulsion systems, as well as disruptive technologies and their supporting infrastructure and how those are going to develop, particularly in urban areas. So those are our 4 research themes. And we operate as a industry consortium. So we have members who pay into our consortium, and then we, working with them, select a rolling portfolio of projects each year. So we currently have 4 research projects ongoing, and we have our 2nd annual call for proposals that is live right now. And we are soliciting new proposals from the faculty across campus.
That's very exciting. I'm looking forward to seeing what the new raft of topics will turn out to be. But I'd like to thank you both very much for these really interesting presentations, and wish you well with your new center. I'd also like to thank everybody who's joined us from around the world, and to also wish you well, and hope that we all remain in good health and get quickly back to work again, and see more of you. Thank you all very much. Bye.